Hello and welcome to GNA University. My name is Burhan Bashir. I'm an assistant professor in the Department of Medical Radiology and Imaging Technology in the School of Allied and Healthcare Sciences. For this series of lectures, we will be discussing about computed tomography, and the series will include the basic physics, instrumentation, generations, and some of the commonly utilized protocols. So first, let's get into the background, why CT was developed, what's the need for the CT, and what are the superior advantages of this imaging modality. Earlier, we had X-ray systems. In the X-ray systems, we are able to image the anatomy of the body, but the problem is that the three-dimensional anatomy is compressed to two dimensions. In most of the diagnosis, it's okay. But whenever it comes for the brain study or whenever it comes to the specific anatomical regions, there when the anatomy is compressed to two dimensions, most of the diagnostic information is lost. Say, for example, we try to study about the brain. With the help of X-rays, we will not be able to study that because the X-rays will be blocked by the cranium bones only. So, to get the image of the brain without actually cutting open the head portion of the patient, we require three-dimensional tomographic image. So, as the name is suggesting, computed tomography means that to create the tomographic or slice images of a body with the help of computer system. So, coming for a little historical perspective, in 1957 to 1963, mathematically we achieved the documentation that we can recreate image of the cross-sectional body by taking multiple projections of that object. But until this time, we did not had any of the machines which were actually able to perform this thing. So this was developed or theorized by a scientist named as Alan Comrak. Then in 1967, we produced first test image in which we were able to achieve the cross-sectional image, that too of brain. Then finally in September 1971, first prototype of CT was installed in Atkinson Modley Hospital in Wimbledon, London. And for that particular reason, the German scientist whose name is Sir Godfrey N. Hounsfield is attributed as the father of modern day CT, because this was the scientist who actually developed the first working model of the CT machine. Then in June 1973, first clinical brain scanner in US Mayo Clinic was used. In 1975, Hounsfield built a machine that was now capable of taking images of the whole body of the patient rather than confined to the brain only. In 1979, both the Sir Godfrey Hounsfield and Alan Comrak were awarded with the Nobel Prize for the invention of the working model of CT. So this was a little historical perspective of the computed tomography. Now, let's talk about generations of CT. So, over the period of time, the CT has got many of the developments, and upon each development is known as a generation. So, this is the classification of computed tomography based on the arrangement of the components, mechanical motion required to collect the data set. So let's talk about the first generation CT. This was the very basic model with which we were only able to acquire the image of the brain, and this was also known as EMI scanner or CAT scanner. The word EMI scanner stands for Electrical and Music Industry, because this was the company which first developed the first working model of CT. Also, it's known as CAT. CAT stands for Computed Axial Tomography, because at this very generation we were only able to acquire and visualize the axial image only. In this particular CT system, as you are able to see from this diagram, we are using this particular thing. This is known as head bath. Head bath is a device or a membrane-like structure in which the head of the patient was kept while we were scanning for the head. The reason is that the first generation CT was using pencil beam. As the pencil beam goes through the wider part of the head, okay, so the beams are not attenuated and we get an image. But if the same pencil beam travels through this particular portion, the narrower part of the head, the beam hardening artifact arises. So to ease out the beam hardening artifact, we use water bath so that we get equal thickness of the head all over the scan. So this is the diagram showing the brain scan using the first generation CT. So the first generation CT is also attributed the name EMI scanners. The reason again is that this particular model or this particular generation of CT was developed by the company which is known as Electrical and Music Industry. So that's why it was attributed as EMI scanner. So how does it work and what was the geometry of this particular generation of the CT? It worked on a geometry that's known as translate, rotate, acquisition. What does translate, rotate, acquisition mean? Translate means whenever we are moving forward the patient with the help of the patient table, and rotate geometry means whenever the detector as well as the X-ray tube rotates around the patient to acquire a particular slice. So how does it work? The patient's head was recessed via rubber membrane into a water-filled tub. The reason is to ease out the beam hardening artifact, as I already described from the previous slide. This device was designed such that the water-filled tub will help to fix the patient head and path length through the patient's plus water for all the rays and the transmission. And if we are using pencil beam and we don't use water path, then the beam hardening artifact will arise in a resulting image, okay, due to uneven thickness of the patient's head. So patient remains in one position, that is the spine position, throughout the scan. The gantry moves in two different motions. One is known as linear motion, second is known as rotatory motion, and also this particular is known as the geometry of the first generation. The linear motion means that we have to forward the patient in a slice thickness increment after every slice is acquired, and the rotatory motion means that both the X-ray tube as well as the detectors revolve around the patient, acquiring data for one single slice. So the detectors that we used in the first generation had a number of 1 or 2. That means in first generation CT only 1 or 2 detectors were used. Both the detectors were sodium iodide detectors, and they were located on the exact opposite side of the X-ray tube. One of the detector measures the transmission of the X-ray through the patient. Second one is the reference detector that intercepts a portion of the beam before it reaches a patient. Then after this data acquisition, we use sophisticated algorithms, or which we commonly know as reconstruction algorithms, which will reconstruct this particular image into a slice. The collimator that we used in the first generation CT is known as pinhole collimator, and as the beam used was a pencil beam, this pinhole collimator ensures that no scattered radiation reaches to our detector and only the straight traveling radiations are registered inside the detector. Here, in case of advantage of the first generation, we have to use water-filled tub that acted to bolus the X-rays so that the intensity of the X-ray beam outside and inside the patient's head was similar, so that no miscalibration will be recorded and also a beam hardening artifact will not arise. So this pencil beam allowed very efficient scatter reduction, because scatter that was deflected away from the pencil beam was not measured by the detectors, as before the detector we were using pinhole collimators. There were some of the disadvantages of this first generation CT. First, it was very slow. To acquire one single slice, we required a time span of at least 5 minutes, and this was used for brain only, as you already know that for the rest of the body we need the patient to stop breathing. The patient cannot stop breathing for this much period of time, so this is the reason the first generation CT was only confined for brain scans. Second, the detectors that we used were hygroscopic. Hygroscopic means they had a nature that they will acquire moisture from the environment, and with that defect what we needed was, after acquiring each slice, we needed to recalibrate these detectors, or after a scan we needed to recalibrate these detectors, and after quite a period of time, say for example 2 or 3 scans, we needed to replace these detectors. Then the next disadvantage is that the resolution of this particular generation was very poor. The total scan time of the first generation CT was very long, and it was about 25 to 30 minutes. This again is a reason that the first generation CT was only confined to the brain scans. So this is a picture showing the cross-sectional image that was acquired by first generation CT. Apart from all of these disadvantages, what was the advantage of using the first generation CT is that we were able to recreate cross-sectional image of the brain, that too for the first time in history, without actually cutting open the patient. Then in the second generation of CT, some advancements were done to the first generation CT. Again, the geometry for the second generation was the same. The translate and rotate motion means the tube and the detector rotated around the patient, acquiring a slice. Then after that, we have to forward the patient using the patient table, and that motion is known as translate motion. Here, the geometry for the beam was changed from pencil beam to narrow fan beam. Means more wider beam was used, and the angulation was about 10 degrees. Now, what's the advantage of using a wider beam? Earlier, if we are using a pencil beam, the pencil beam will cover up a small anatomical region. While we are using a fan beam, that will cover up large anatomical region, means in lesser time we will cover up the whole region of interest. Here for the detectors we used multiple detectors or linear array of the detectors, and mostly the number was 30. In first generation we were using 1 to 2 detectors. So using more number of detectors means we will be able to acquire the data from our region of interest, that too within less time. So how does it work? The working principle of second generation was same as that of the first generation, as the patient remains in one position, that is spine position, and the machine will move in 2 different directions. The 2 different directions are rotate and translate motion. Now the linear motion and the rotatory motion, translation, linear motion, it repeats over and over 60 times, and it will require 180 degrees image acquisition. Rotatory motion, between each of the linear motion, the rotatory motion between each of the linear motion gantry rotates 3 degrees rather than 1 degree in first generation. The reason is we are using fan beam, and fan beam is able to cover up larger area as compared to the pencil beam. So this is a diagram showing the working of second generation CT. Here we are using a fan beam. Apart from that, we are using multiple detector array. Now, what were the advantages of the second generation? Here we had reduced scan time. Compared to the first generation CT, where the total scan time was about 25 to 30 minutes, in the second generation CT, the total scan time was reduced to 90 seconds. With the reduced scan time, we were now able to image the whole body rather than confined to the brain scans. Now coming to the disadvantage, again the detectors that were used were sodium iodide detectors, and those detectors have hygroscopic nature. Means while we were working on them, they would acquire moisture from the atmosphere, and with which a miscalibration will happen to the detectors, and they will require a regular recalibration. Even after a few uses, we needed to replace these detectors. The next disadvantage is scattered radiation due to fan beam. The next generation of the CT is the third generation. In the third generation, we shifted from the traditional rotate translate geometry to the new geometry that was known as rotate acquisition. In the rotate acquisition, the X-ray tube and the detectors both moved around the patient. Helical scanners are based on the modification of this rotate scanner design that will come up in upcoming slides. The first and second generation had to be dynamically recalibrated at the end of each translation, as we were using very basic models of detectors. But in third generation CT, we used more advanced detectors. Those required less maintenance and less recalibration. For faster scan, we required to eliminate the translate motion, and we used only rotate motion. As far as geometry of the third generation is concerned, we use a wide fan beam, and the angulation for this particular fan beam was about 50 to 55 degrees, and it covered entire patient. Now again, if we increase the angulation of the radiation, then more area of the anatomy will be covered within single rotation. That eventually will reduce our scan time. Here, if we talk about the number of detectors, in second generation, the number of detectors that we used was about 30. In third generation, it ranged about 500 to 1000 detectors, or if we talk about a particular number, it's approximately 750 detectors. Again, by increasing the number of detectors, we are significantly reducing the scan time. And they are placed in an arch shape around the patient. Tube and detector both rotate together around the patient, and that's how we acquire the image. So this is a diagram showing the third generation geometry that's known as rotate geometry. Now, what were the advantages of the third generation? One of the advantages was no translation motion was required, and this significantly reduced the scan time. One of the disadvantages of the third generation is that both the detector as well as the X-ray tube are rotating, and if one of the detector is miscalibrated or goes out of function, that eventually in our resulting image will give rise to an artifact which is known as ring artifact. So there are multiple artifacts in CT, but one particular artifact that's known as ring artifact is particularly associated with the third generation of CT because of its geometry, which is known as rotate geometry. Now if we are using more wider beam, that means more scatter radiations will arise, and here in one of the advantages, the total scan time was reduced to 5 seconds. Then the next generation of the CT is known as fourth generation. Fourth generation was particularly developed to eliminate the error that was encountered in third generation CT, and that's known as ring artifact. So talking about the geometry of the fourth generation, the geometry is known as rotate stationary geometry. So instead of moving both the X-ray source as well as the detector, we will move the X-ray source only and we will keep the stationary. So instead of moving both the X-ray tube as well as the detectors, we will move only the X-ray tube and we will keep the detectors stationary, placed around the patient in a ring formation, and that's what the rotate stationary acquisition means. So rotate the X-ray tube and stationary detectors all around the gantry. Now in this particular geometry we were using even larger fan beam. So increasing the fan beam increases the area coverage and that significantly reduces the scan time. But it comes with a disadvantage that more scatter radiation will be there, and to deal with that, in fourth generation we used a special type of filter that was known as bow tie filtration. Now if we talk about the number of detectors used in the fourth generation, the number of detectors was usually around 4,800 fixed detectors. This generation was designed to overcome the problem of ring artifact, and the detectors are removed from the rotating gantry and placed stationary 360-degree ring around the patient. So this is the diagram depicting the fourth generation geometry, in which you are able to see that the only moving thing is the X-ray tube, and here in the 360-degree format the detectors are placed all around the patient inside the gantry. So it uses a detector fan, a fan beam. Data are acquired by a single detector over a period of time, and that requires for the X-ray tube to rotate through the arc angle of the fan. Advantage: no cable wear and tear. In the earlier models, both the X-ray tube and the detectors were moving, means during the time of acquisition or during the time of rotate motion, both wires were winded and unwinded around the fulcrum. Now if we have kept the detectors stationary, the only cable that will be winded and unwinded will be from the X-ray tube, and that will significantly reduce the cable wear and tear. Second advantage: as the ring artifact was observed in third generation CT due to the rotate motion, that was eliminated by the rotate stationary geometry. Here we are using more number of detectors, we are using more wider fan beam, that eventually will lead to lesser scan time. Let's talk about the disadvantages of the fourth generation. Here in the fourth generation, higher patient dose was observed because we were using more wider fan beam, which will eventually result in more scatter radiation. Here increased scatter radiation is due to the large fan beam. Up to the fourth generation, we were able to image the whole body except one anatomical region, that's known as heart. So for the imaging of heart particularly, we introduced fifth generation CT. Fifth generation CT had geometry of stationary acquisition, means both the X-ray tube as well as the detectors were stationary in this particular generation of CT. Here instead of X-ray tube, what we were using was electron gun that emitted electrons, and no moving parts of the scanner gantry were there. Instead we had a large arc of tungsten rings, and they were directly opposite to the detectors. As you will be able to see from the diagram, this is the diagram of the 5th generation CT. So instead of moving parts and a gantry, what we have is on the lower aspect, there are the detector rings or the tungsten rings, and onto the opposite side is the detector rings. On this part, this is the electron gun. It will produce the electrons. Those electrons will be directed towards these tungsten rings, which will be able to produce the X-rays, and those X-rays will be directly taken up by these detector rings. So the electron beam is produced in a cone-like structure, a vacuum enclosure behind the gantry, and is electronically stirred around the patient so that it strikes the annular tungsten target. What were the advantages? As said, in earlier generations we were able to image the whole body but not the heart, because we cannot stop the motion of the heart, and if we use the earlier generations like the 3rd and the 4th generation for the imaging of the heart, there we acquired an artifact which is known as motion artifact. Here, by using the 5th generation, the scan time is significantly reduced, and this allows us to visualize the heart and major vessels. For most of the times, the 5th generation was specifically designed for the evaluation of the heart and great vessels. What about the disadvantage of the 5th generation? We had space constraints. Means the 5th generation CT was only able to image a little portion of the anatomy. That little portion was only heart. So if any anatomical region was larger than that, it was not imaged using 5th generation CT. One of the other names of the 5th generation CT that you will read in some of the text is known as SINE CT or electron beam scanner. So the acquisition time in the 5th generation CT was so much less that we were able to image the heart in actual motion. That's what the SINE CT means. So this again is the diagram for the 5th generation CT. The next generation is known as 6th generation of CT. The 6th generation CT is also known as single slice, helical or spiral CT. So the first helical CT that was developed and was clinically used was in the year 1989. So through 3rd and 4th generation CT scanners, we eliminated the translation motion, but gantry again had to stop because the X-ray tube was again utilizing the wires. So we had two motions going on there. One was the acquisition motion, in which the wires were winding around the gantry, and we had to stop to unwind the wires to be able to acquire another set of images. In 6th generation CT, we introduced a technology that's known as slip ring technology. The slip ring technology eliminated the use of the wires and allowed the X-ray tube to be continuously rotated around the patient. So in this design, the X-ray tube and the detector both rotate around the patient as the patient is moved through the translate motion smoothly into the X-ray scan field, and data is acquired. So instead of acquiring one single slice, we are acquiring volumetric data. This produced one continuous volume set of data for the entire region of interest. The entire scan can be done with one single breath hold, which was earlier done in slices version. So this is a diagram showing the volumetric data acquired by the helical or spiral CT. So instead of taking single slices and adding them together, we start at one place. Due to the continuous motion of the X-ray tube and the detectors, we are able to acquire the volumetric data, and in one single breath hold, we can image the whole region of interest. Next is known as detector pitch. It defines as the table movement translate per rotation divided by the beam width. Means how much slice thickness we have set and plus how much the table is moved after one single slice acquisition. So if the beam width or the beam collimation is 10 mm and the table moves 10 mm, we say the pitch for this particular scan is 1. Similarly, we can increase or decrease the pitch, that eventually will increase or decrease our data acquisition. Now, what were the advantages of the 6th generation? First, the slip ring technology was used, smoother table movement was there, software adjustments for the table movement were required because we were doing continuous acquisition, more efficient tube cooling was required because in earlier designs we were acquiring one single slice, then the tube was at rest. Now in this continuous acquisition, the tube is currently producing exposures, so we require more efficient tube cooling. Again, while we are doing continuous acquisition, we require more efficient detectors. What were the advantages? The advantages are the patient and the system movement are continuous, entire abdomen or chest can be imaged within 30 seconds, and that will eventually reduce the motion artifact. The next advantage is that we have availability of volumetric data and increased beam width of 40 mm. Disadvantage, this was less scan rejection and the setup for the 6th generation was very expensive. So this is the diagram showing the 6th generation. Coming to the last, this is known as 7th generation of CT. In the 7th generation, we call this as multi-slice multi-detector CT. So what does multi-slice multi-detector means? Earlier, from generation 1 to generation 6, in one single scan, we were only confined to one single slice because we used only one single array of detectors. But instead of that, if we use multiple detector arrays, so that it means that during one single scan, rather than acquiring one single slice, we will be able to acquire multiple slices. So that is what means the multi-slice and multi-detector CT. It was introduced in the year 1998 and it uses the same principle of the 6th generation, that's known as helical scanner. Geometry here, the cone beam is used and the total z-axis of the X-ray beam width is used. The detectors that we use in the 7th generation are the most advanced, which are known as solid state or multi-detectors, which are placed in multiple rows, and the number of rows are approximately 4. As we are using multiple detector rows, that means during one single scan we will be able to acquire multiple slices during one single tube rotation, and we will cover more volume of the patient than the earlier 6th generation. The collimator spacing is wide and more of the X-rays that are produced by the tube are used in producing the image data. Now, opening up the collimator in a single array scanner increases the slice thickness, reducing the spatial resolution in the slice thickness dimensions. With multiple detectors that we are using in 7th generation array scanners, the slice thickness is determined by this detector size rather than the collimator size. Beam pitch, again, this is the table moment in one gantry rotation divided by the slice thickness. Now, there are different types of CTs. One is known as single slice, second is known as multi-slice. So, as far as the resolution is concerned, the single slice CT has lesser resolution as compared to the multi-slice CT. For the noise is concerned, in single slice CT the noise is high as compared to the multi-slice CT. Motion blur means whenever we are acquiring the image, where will be the motion artifact mostly encountered, it will again be encountered in single slice CTs rather than the multi-slice or multi-detector CTs. Partial volume artifact, that is one of the artifacts, arises more in multi-slice CTs rather than the single slice CTs. So here is a diagram representing the 5th, 6th and 7th generation of CT. So this was about the CT generations In the next video, we will continue about CT instrumentations. Thank you so much.